In this video, I will show you the things that you need to memorize from Unit 3 of AP Calculus AB. We learned some new derivative rules in this unit. For example, the derivative of e to the something is still e to the something. But if the exponent is not an x, you have to use the chain rule and multiply by the derivative. We also learned that the derivative of natural log is 1 over something. If this is not an x, again, we have to do the chain rule and multiply by the derivative. All right, this is similar to e to the u power. All right, but it's a to the u power. So notice how the derivative of e to the u power is still e to the u power. Well, guess what? The derivative of a to the u power will still be a to the u power. But because it's not e, we have this extra piece to it where we multiply by the natural log of a. So you just have to memorize this. And again, if the exponent is not an x, then you have to do the chain rule and multiply by the derivative. Now, the derivative of log base a of u is going to be 1 over u. Remember when we had the derivative of natural log and it was 1 over u? Well, the derivative of a regular log is still 1 over u, but we're going to need this extra modification where we have the natural log of a also in the denominator. And because this is a u and not an x, we need to do the chain rule and multiply by u prime. Speaking of things you need to memorize from Unit 3, make sure you have memorized this chart of graphical relationships between f, f prime, and f double prime. My recommendation is that before your next quiz or test, you quickly write this chart on a piece of scratch paper or in the margin of your test and use it for the test. So let's talk about justifications. If you wanted to justify why function f is increasing, we know that function f will be increasing when f prime is positive. So here's the easiest way to justify. F is increasing because f prime is greater than 0. But you could also put f prime is positive because that means the same thing. If we want to justify why f is decreasing, well, that will be because f prime is less than 0. Or if you wanted to write it the long way because you have all kinds of extra time, you could write f prime is negative. So how would I justify why f is concave up? Here's a hint. When you talk about concavity, you really want to refer to the second derivative. Looking at the chart, we know that f will be concave up when f double prime is positive. So the easiest thing to write is f is concave up because f double prime is greater than 0, which of course means that f double prime is positive. Similarly, we will justify that f is concave down because f double prime is less than 0. In other words, f double prime is negative. POI stands for point of inflection. This is where the function changes concavity. For example, if a function is concave up and then it switches and becomes concave down, the point where it changes from concave up to concave down is the point of inflection. But if the function is going from concave up to concave down, that means that f double prime is going from positive to negative. Of course, we would also have a point of inflection if the original function went from concave down to concave up. In other words, if f double prime went from negative to positive. We will justify that f of x has a point of inflection because f double prime changes signs. How do we justify f has a relative maximum at x equals a using the first derivative test? We learned that f will have a relative maximum at x equals a if the function is increasing to the left of a and then decreasing to the right. Wherever function f is increasing, f prime will be positive. Where function f is decreasing, f prime will be negative. So if there is a relative maximum at x equals a, that means f prime should be going from positive to negative. So to justify, we would say that f has a relative maximum at x equals a because f prime goes from positive to negative. Similarly, we see that function f has a relative minimum at a if the function is decreasing to the left of a and increasing to the right. But that means that f prime goes from negative to positive. So f has a relative minimum at x equals a because f prime changes from negative to positive. Again, this is called the first derivative test. But there is another way to justify that we have a relative maximum at x equals a. There are two parts to it. First, we have to say that f prime is equal to 0 at x equals a. That means that we have a horizontal tangent line. But then we have to say that f double prime is negative. That guarantees that the function is concave down, which creates this local maximum. So we can justify by saying f has a relative maximum at x equals a because f prime is equal to 0 and f double prime is negative. Because this method involves f double prime, we call it the second derivative test. Look back at this picture. I'm going to change one thing. I'm going to leave f prime equal to 0, which means we will still have a horizontal tangent line. But I'm going to change f double prime from negative to positive. If f double prime is positive, that means the function must be concave up. Now we can see that the point of tangency is a relative minimum. F has a relative minimum at x equals a because f prime is equal to 0 and f double prime is positive. For the rest of this video, let's talk about motion justifications. In other words, let's talk about position, velocity, and acceleration. If an object is at rest, that means that the velocity is equal to 0. Velocity is the derivative of the position function, so you might see this written as x prime is equal to 0. How would we justify that an object changes direction? Well, the sign of the velocity indicates the direction. If the velocity is positive, it means that the object is moving to the right or up. If the velocity is negative, it means that the object is moving to the left or down. If an object changes direction, we will know because the velocity changes signs. So if the velocity goes from positive to negative or from negative to positive, we know that the object is changing directions. There are three ways to justify how we know that an object's speed is increasing. First, we know that an object's speed is increasing when the velocity is positive and increasing. So if the velocity is positive, that just means that the object is moving to the right. But if the velocity is increasing, that means it's getting faster and faster and faster. So the object's speed is increasing. The second way to know that an object's speed is increasing is if the velocity is negative and decreasing. This can be a little bit confusing. If the velocity is negative, that just means that the object is going to the left or down. But if the velocity is also decreasing, that means that the object is going faster and faster and faster to the left. Here's why. Imagine that the object is going to the left at negative 10 meters per second. And then it's going negative 20 meters per second. That's actually a decreasing velocity because negative 20 is less than negative 10. If we then go to negative 30 meters per second, negative 30 is less than negative 20. So the velocity is decreasing, but you can tell that it is speeding up to the left. Negative 10 meters per second, negative 20 meters per second, negative 30 meters per second. Negative 30 meters per second is faster than negative 10. It's just that it's all going to the left. The third way to know that an object's speed is increasing is if the velocity and acceleration both have the same sign, which means that they're sort of working together. If the velocity and acceleration are both positive, for example, that means that the object is going faster and faster to the right. If the velocity and acceleration are both negative, that just means that the object is going faster and faster to the left. But again, the speed will be increasing because the velocity and acceleration are sort of working together. For comparison, an object's speed is decreasing when the velocity and acceleration have opposite signs. If one is positive and the other is negative, then these are sort of working against each other. In this case, if the velocity is positive and the acceleration is negative, that means the object is moving to the right, but it is slowing down. Another way to know that an object's speed is decreasing is when the velocity is positive and decreasing. It's moving to the right, but it is slowing down. This last one is a little more counterintuitive, shall we say. The object's speed will also be decreasing if the velocity is negative and increasing. So if the velocity is negative, that means that the object is going to the left. But if the velocity is also increasing, that means, for example, imagine that we're going from negative 30 meters per second, negative 20 meters per second, negative 10 meters per second. Technically, I'm describing an increasing velocity because negative 10 is greater than negative 30. Okay, negative 10 is further to the right on our number line. So, going from negative 30 to negative 10 is an increasing velocity, but clearly when you're talking about speed, negative 10 meters per second is slower than negative 30. So if you can understand the concept that I was just describing, great. Otherwise, you can just memorize the following. When the velocity terminology sounds contradictory, then the speed is decreasing. So can you hear how positive and decreasing? That sounds sort of contradictory, so you know that the speed is decreasing. Negative and increasing. That sounds contradictory. The speed is decreasing. Compare that with positive and increasing. Those kind of sound similar. That's when the speed is increasing. Negative and decreasing. Those sort of sound the same. So that's how you know that the speed is increasing. All right, guys, those are the main things you need to memorize from Unit 3.